I use my TOA, right? I go back to my trigonometrical function TOA, which is tan theta equal opposites. So my opposite is AY, right? AY over adjacent. My adjacent is AX, right? So now to find theta, I'm going to be saying theta equal tan inverse of equal tan inverse AY over AX. Now, this is if I'm looking for the angle of vector A, right? Now, because I have resultant vector in the x component and in the y component, so if I'm looking for my total angle, it will be tan theta equal ry over rx. So whereby therefore my theta will then be tan inverse of my ry, my resultant vector in the r component, and my resultant vector in the x component. Okay, so I believe we actually understand this. So I'll see you guys in another lesson. Hey guys, my name is Daniel. Today we'll be talking about vectors mechanics 1, more like an introduction to vectors. Alright, let's get started. What are vectors? Vectors are quantity or quantities that have both magnitude and direction. Alright, vectors are quantities that have both magnitude and direction, right? So they are commonly used in physics to represent various physical quantities such as displacement, velocity, force, and acceleration. All right, so vectors can be reduced or splitted into components. Okay, so the components of a vector are the projections of the vector along the coordinate axis. All right, so for example, we have vector v. Okay, so v can be splitted into two components, which is vx plus vy. All right, so this vx and vy talks about the component of vector v along the x-axis and along the y-axis. Now let me draw a Cartesian plane. So as we know, this is x-axis and this is y-axis. All right, and then the resultant is v. Let me draw the resultant this way. The resultant is v. Okay, the horizontal, which is the x-axis, can also be called vx. So vector v is splitted into a component called vx along the horizontal axis, and also can be splitted into vy along the vertical axis. Okay, so this is how we got our vector components. All right, So moving on, vectors there are methods, right, to resolve a vector. There are methods to resolve a vector. So we can use the graphical method, right? We can also use the Cartesian coordinates, and 3, we can also use the polar coordinates. Okay, so these are methods we can use to resolve a vector in different forms. Okay, so every method has a specific way of adding or resolving a particular vector. Okay, so talking about the graphical method, right? The graphical method is talking about we having a vector that has been illustrated by lines and arrows, and then resolving it. Now, for example, we have what is called the parallelogram law, the parallelograms law of vector, which states that if two vectors are represented by the adjacent sides of a parallelogram, then the diagonal drawn from the point of intersection represents the resultant vector in magnitude and direction. Now, for this is what I'm talking about. Let's look at the graphical method. Okay, so if we have a parallelogram, right, and we know that these sides are equal, these sides are also equal, moving upward. Okay, so here let me say this is the horizontal direction. So I can say, let me use F. I can say this is Fx, then I have my arrow at the top, and I can also say this is Fy because it's moving along the vertical axis, right? Now, for me to have or get the resultant force, then I have to draw a diagonal through the center of the parallelogram, right? And this becomes my resultant force. So which means that if I add these two together, I'm going to be getting a vector Fr. Okay, so if this is the vertical axis, if the vertical axis is Fy, then this side also should be Fy because this side is equal to this side. So I'll have Fy here. And same thing for this. If this is Fx, this side should be Fx also. So Fx. So we can see this is a graphical illustration. Now I can now resolve these forces, or better draw this diagram in a simpler form by using what is called head-tail method, right? Or tip-to-tail method. Now I see that the horizontal axis is moving towards this direction, right? So I can move this arrow to the tip, right? So I'll have something like this. My arrow is now at the tip, so I have Fx, right? And then I can move this arrow also to the tip. And remember that the horizontal starts from this point. So I go this way, I put my arrow at the tip. So this becomes my F, right? And then my resultant force, right? I join it, and then I have my FR. Right, now this is much more simpler and understandable, right? So this method is what we call the graphical method, or we can call it the head tail method. So where this horizontal vector stopped, right, the vertical vector continued from there. So this is the head, and this is the tail of the vertical vector. I hope we understand that. Okay, so these vectors can actually be resolved using two rules. And what are these rules? They are called the sine rule, right, and the cosine rule. Okay, probably I'll make another video talking about the sine rule and the cosine rule. Okay, now let's move to the second method of resolving vectors, which is the Cartesian coordinates, right? The Cartesian coordinates. So the Cartesian coordinates, this is also talking about resolving force, or resolving a force using coordinates x, y, or z. So in the Cartesian coordinates, we have two-dimensional Cartesian coordinates and three-dimensional Cartesian coordinates. Okay, let me put that down. So we have two-dimensional Cartesian coordinates, and we have three-dimensional Cartesian coordinates. So I'll explain this too. Okay, so let me use a diagram. Okay, so if we have, okay, let me go back to this. So if we have x-axis, right, if we have a Cartesian plane x, and this is y, right? Now in this form, this is two-dimensional Cartesian coordinates, right? So in this case, we have, let's say we have our resultant vector to be our vector to be A. Now if I'm resolving this vector into two components, right, then I'm supposed to have AX, right, plus AY. Is that not? Now, using Cartesian coordinates, my x is also represented as I, and my y is represented as J. Okay, so if I'm resolving this, if I'm resolving vector A, then I should be having A equal AXI plus AY j. Right. So this is what? Two-dimensional Cartesian coordinates. Okay. So for three-dimensional coordinates, now coming back to this diagram, we are going to be assuming that there is another coordinate at this point, which is the z coordinate, right? And what is allocated to the z coordinate? K, right? So x coordinate I, y coordinate j, z coordinate k. So if I'm resolving vector A, right, into three-dimensional coordinates, right? So I'll have A equal AXI plus AYJ plus AZK, right? So this is what? Three-dimensional Cartesian coordinates. All right, I hope we understand that. And it is actually very, very simple. Very, very simple. So if we are adding these vectors together, okay, in terms of vector addition, right, where we have a vector A, where we have vector A equal AXI plus AYJ plus AZK, and we have a vector B which is equal BXI plus BYJ plus BZK. So finding the resultant vector, which is R, so I can say my resultant vector R equal these two vectors, right? So which is A plus B. I hope we got that. So I have vector A and vector B, which are equal this, and then my resultant vector, which is the addition of these two vectors, is equal A plus B. Now, finding my resultant vector, R will be equal. Now, I'm going to be taking, I'm going to be putting together the vector components that are common, right? I'm going to be adding together the vector components that are common. So I have AX here and I have BX here. So I put these two together. I have AY and BY. I add these two together. AZ and BZ. I add these two together. So I'll be having these two, that is AX plus BX, then my I. So I'm factorizing the I, right? Then plus A and B. So this will be AY plus BY J, and then plus AZ plus BZ K. Okay, so this is how I get my resultant force. Now, I can also split it. I can first of all add the vector A and vector B together for simplicity. That is, if you don't understand this method. Okay, or I can say my vector R, since my vector R is my resultant vector r is equal a plus b, so I can add all of the a and b together. So I can say my a is axi plus ayj plus azk, right? This is my a. Then plus b, right? So what's my b? Bxi plus byj plus bzk, right? I see here that I'm going to open the bracket. So opening the bracket, I have axi plus ayj plus azk plus bxi plus byj plus bzk. Now, what next? I'm going to collect like terms. So I have axi and bxi, right? So these are like terms. Exactly. So they are of the x-axis or the x component. So I'm going to be collecting them together. So I'll have my r will be equal axi plus b. Oh, sorry. I'm going to be factorizing the I actually. So let me take this again. R equal ax plus bx. Then I factorize the I, right? Plus the y-axis, the y components, right? Ay plus byj plus az plus bzk. So this is it. So but this, the first one I did is kind of faster, right? So I decided to break it down in case you really don't understand how we got this, or you didn't get the method I used. But this is, we are still at the same final destination. All right. So moving on, let's go to the polar Cartesian coordinates. All right. So talking about the polar Cartesian coordinates, this is where this is being represented by the magnitude of a vector and angle using trigonometric functions. Okay, so let's talk about this quickly. So I have polar coordinates. Okay, so in polar coordinates, we are going to be introducing the trigonometric relationship here. So for my let's say I have vector A, right, and B. Okay, so for my vector A and B, I'm supposed to have a coordinate A. For vector A, I'm supposed to have a coordinate A, which is the magnitude, and theta, which is the angle. Then for B also, I'm supposed to have a magnitude B and the theta for B. That is the angle for B also. So, and I'm putting it as theta 1 for A, theta 2 for B. So if I'm resolving these two vectors, remember that the resultant vector is equal A plus B. Okay, so resolving vector A into two components, right? I'm going to be using what is called an abbreviation called SOHCAHTOA. Okay, now let me draw this. Let me use the Cartesian plane again. So I have x, I have y. Right. Now resolving resultant vector A. right? Resolving vector A. So if I'm resolving vector A, okay, this is vector A, right? So if I'm resolving it into two components, right, which is the x component and the y component. So my x component for vector A will be ax, and my y component for vector A will be ay, right? So and remember, I'm supposed to have an angle, right? So my angle is what? Theta 1. Okay, so I think that is clear. So if I'm resolving for x, it means that or let me say, if I'm resolving for component x, I'm going to be using the car. Now the car is talking about cos theta equal adjacent over hypotenuse. Adjacent over hypotenuse. So this is my adjacent, this is my hypotenuse, and this is my opposite. Okay, so I want to resolve ax, or I want to find ax, right? So because I'm looking for ax, I'm going to be taking the hypotenuse and my angle, right? So and the trigonometric ratio that can help me find x in this manner is cos theta or cosine theta. Okay, so resolving this, I would have cos theta 1, because my theta is theta 1, or my angle is theta 1, equal adjacent, so which is ax, over hypotenuse, which is a, right? So remember that I'm trying to look for ax, so I'll make ax subject of formula by cross multiplying. So then I have ax equal a cos theta 1, and here I have it. This is my ax. So this is my vector component x. So the same thing for the y-axis, the y component, right? For the y component, if I'm looking for this, right, I'm going to be if I'm looking for the y component of vector A, so I'm going to be taking the hypotenuse and my angle. I'm going to be taking the hypotenuse and my angle. All right, so the trigonometry ratio that can give me this is the SO, right, which is the sine theta equal opposite over hypotenuse. Okay, so here I have sine theta 1, right? That's my angle, which is equal opposite. This is my opposite, so which is ay, and my hypotenuse, which is a. So remember that I'm trying to find ay, so I cross multiply, right? I make ay subject of formula. So then I have ay equal a sine theta 1. Okay, so now let's put these two together. So we are able to find that ax is equal a cos theta 1, and ay equal a sine theta 1. So I think we are good with that. Right. So this is how we got all of this using trigonometric function. Okay. So which means a vector can be resolved into two components, x and y. So if we'll be doing the same for vector b, so we already know that we don't need to start all of this all over again. So we already know that for bx, it is going to be b cos theta 2, because the angle for b is theta 2. And for by, it's going to be b sine theta 2. So it's as simple as that. I hope we got that clearly. Now, finding the resultant of the y component and the x component. Okay, so we have to find the resultant of the y component and the x component before we get the total resultant. Okay, so y, remember we are working on vector a and b, right? So vector a has its own y component and x component. Vector b has its own y component and s component. So we have to look for the resultant, right? The addition of all the x components we have, both a and b, and the resultant vector of all the y components we have, both a and b. So I'll call the resultant, to find the resultant of the s component, I'll say rx, so which will be equal ax plus bx. So I remember that ax is equal a cos theta and bx theta 1, and bx is equal b cos theta 2. So in real world, b is a number, right? Theta is also an angle. So I'm just going to calculate this to get my bx, and then it gives me a value. Okay, so for the y resultant of the y-axis or the y component, I have ry equal ay plus by. It's as simple as that. So for me to get my resultant or total resultant, or magnitude, it can also be called magnitude, right, of resultant x and y, right, I'll be having r, which is the total resultant, equal. So here I'm going to be using what is called the Pythagorean theorem. So r equal square root rx all squared plus ry all squared. So this is how I get my total resultant vector, right? And also, if I want to get my direction or the angle, or let me say the total angle also, remember that we have theta 1, theta 2. So if I want to get the total angle or the direction of my vectors, then I